In this video, we are going to go over how to create graphs based on the results of a Nastran random analysis. Now, in the first part of the video, I'm going to quickly create the graphs. And then in the second part of the video, I'm going to explain how I created these graphs. So generally, what you do is you open the HDF5 Explorer, you upload the H5 file that contains the results of the random analysis. And then here we're going to select the acceleration data set, and we're going to get data for node or grid 111. We're going to click create plot. And then here for this new graph, we're going to say display the accelerations for the Z component or the third degree of freedom. And this is the plot. This is the plot of the power spectral density function values for the third degree of freedom or the Z component. And now let's go ahead and discuss in more detail how do we get this graph. Now, today we're going to be using a few tools. We're going to be using the post-processor web app to create these graphs. The post-processor web app is free as long as you're an MSC Nastran user. If you're a professional engineer, if you're a researcher, if you're a professor, or if you're a student, these tools are free for you to use. Now, the post-processor web app is only compatible with MSC Nastran. If you are using some other type of Nastran, this tool is not compatible with other types of Nastran. It's only compatible with MSC Nastran. Now, if you want to start using these tools today, if you want to download your own installer and use that on your own workstation, you can go to theengineeringlab.com. Here in the top right hand corner, there's a blue button. Click that button, fill out the form, and we'll go ahead and send you a link to download the software. Now, today's examples are going to come from the MSC Nastran Dynamic Analysis User's Guide. If you go to Chapter 8, which is the chapter regarding random analysis, in that chapter, you're going to find a few examples. We're going to go over both example 1 and example 2. Now, in example 1, that example is going to be titled Cantilever Plate Subjected to Base Input in 3 Directions. Now, in this example, what they want to create is a graph for the acceleration, specifically the power spectral density function values, at node 111 in the TZ component of acceleration or the third degree of freedom. So that's the graph. Now, here on my desktop, I already have that bulk data file. I've already performed the random analysis. You can see a few things. Number one, this is configured to perform a modal frequency response analysis. So whenever you perform a modal frequency response analysis, your values are going to be either real, imaginary values, or they're going to be magnitude or phase values. Now, when you perform a random analysis, these are not going to be complex values. So again, when you perform a modal frequency response analysis, you get complex values. But when you perform a random analysis, you do not get complex values. So that's one important distinction I wanted to make up front. Now, when you look through this case control section, you see that they are outputting the accelerations with the acceleration command, and they're outputting the stresses with the stress command. So here, this command is read as follows. Output the accelerations, plot or output the results to the H5 file. So this first argument means the following. Plot. Output the complex values to the XDB OP2 or H5 file. For the second argument, our print, that is saying the following. Output the random analysis results to the F06 and results file. So this would be the XDB OP2 or H5 file. And then the final argument, PSDF, there are different quantities for the random analysis you can output, but here PSDF stands for power spectral density function values. And then at the end of the command, you can see that it's pointing to list 907. So here's list 907. This list consists of 2 node IDs, so nodes 105 and 111. So it's saying output the data for nodes 105 and 111. And now let's go ahead and read the second output command. Output the stresses, both the complex values and the random analysis values, specifically the PSDF values, and do this for list 908, which is corresponding to elements 1 and 5. So if we look back here at the HDF5 Explorer, so let's go ahead and open a new window. Let's go ahead and upload the H5 file. And let's go ahead and look at the acquired dataset section. So here in the navigation bar, let's go ahead and click on acquired dataset. And we have a few datasets available. The complex datasets are the modal frequency response values. Remember, that was controlled with the plot argument. Now we have other datasets available. You notice that this dataset just says acceleration. These are controlled with the rprint values. So these are going to be the random analysis results. And here, these are going to be the modal frequency response complex values. So again, the datasets ending with CPLX, standing for complex, these are output for the modal frequency response analysis. For the datasets without CPLX, those are coming from the random analysis. So you can see that we have stresses from the random analysis, and we have accelerations for the random analysis. Now let's go ahead and confirm one thing. When we look at the F06 file, we have a table. This table is going to be the accelerations for the random analysis, specifically the PSDF values for node 105. So if you look at this line, it says point ID 105. And then if we scroll down a little bit more, we get a second table. So this is going to be the accelerations for node 111. So if we want to, we can go ahead and select the acceleration data set. We can type in both of those node IDs or grid IDs, node 105 and 111, click acquire data set and click create plot. And then here in the navigation bar, click last plot added. Here we're interested in only the third degree of freedom, or the Z component of translation. Here, click on options, select log, and now we're looking at the data for node 105 and 111. Now, for node 111, let's go ahead and display the max peaks. Let me go ahead and make sure I've done this correctly. Here, this first line is not visible, but the second line is visible. So you can see that if I turn this off and on, I get the peaks. Now, if I zoom in very carefully, I get told that the max peak is happening at 31.7 hertz. So if you go to this table, let's go to 31.7 hertz, which would be this line. And let's look at the Z component of acceleration, or the third degree of freedom. And if we look in column 3 at 31.7 hertz, we get the same value, 8.5 times 10 to the 6. And here's the same peak value. Okay, great. So we have confidence that these graphs are using the data that we see here in the F06 file. Now let's go ahead and take a look at another thing. Maybe we want to look at the stresses in the elements 1 and 5. How do we do that? So if we go here, we'll go ahead and select the stress quad 4 data set, and we'll select elements 1 and 5. We'll go ahead and click on acquire data set, click create plot, and here we'll click on last plot added. Here we're interested in the force along the X element axes. Let's go ahead and select the log scale for the vertical axes. And now these are the random analysis results for the element stresses, specifically the power spectral density function values. And then if we wanted to, I don't know if we actually outputted it, or I think we did. Yeah. So if we look here, these are the values for the stresses and the 2D elements. Let's go ahead and do this. Maybe for element 5, so this is element 5, let's go ahead and plot the maximum peaks. So here if we look, the maximum peak is happening here at 31.7 hertz. So if we go to element 5, so this is element 1, element 5 is here, and we want to go to 31.7 hertz. So that would be here. And now let's go ahead and look at the first component, which is the force along the axes of the element coordinate system. So here we get a value of about 2.7 times 10 to the 5. And you notice that's the same value that we see here in the graph. So again, the values that we see in the F06 file are the same values that we see here in the graph. Now, a few other comments regarding these plots. So let's go to the acceleration plot. You could do a few other things here. You can move the horizontal, you can move the vertical axes, you can change the range. So here maybe you want to go from 800 hertz to maybe 900 hertz. What I do is I click on the corners and then I type the value that I want. Now for the lower and the upper bound of the vertical axes, it's the same thing. You could say, hey, let's go from 1E5 to maybe 1E. Here, let me do this again. 1E5 to maybe, let's see, 1E4. And so now I've done that. You can control what graphs to display with the legend in the top right hand corner. You can zoom in and out. If you wanted to, you can take a screenshot of this. So let's go ahead and take a screenshot. You could put that in a report, or here in the top right hand corner, there's a blue button. Click that button and you've downloaded an image of the graph. Here in this other table, view filters and plotted values. All the data that's plotted for this graph or XY plot is in this table. So data for 10 hertz, 10.9 hertz, 12 hertz. Here in the top right, there's a download CSV button. Click that link. And now you have the same data in Excel. Here, let's go ahead and create a quick graph here. And let me make sure I'm selecting the data from 10 hertz all the way to, I believe it's 1000 hertz. And then here, let's go ahead and expand the size. Let's go ahead and select the log scale for the vertical axes. And let's go ahead and redo this for the vertical axis or horizontal axes. We want to use a log scale also. And then for the minimum value for the horizontal axis, we want to use 10 hertz. So here's the same graph in Excel. And now let's continue on in the case control section. So again, the acceleration and stress commands, they control the output of both the modal frequency response accelerations and stresses and the random analysis results. And now if we look further down, there is another section here, the commands for Nastran's XY plotter. Nastran actually has an XY plotter of its own. Here we're only using the XY print to output the same values. Here in this line, we're saying print out the acceleration, specifically the power spectral density function values for node 111 for the T3 component. Now, if you scroll down a little more, you get another table here. Here's that table. If you look at this line, it's saying that these are the values for the acceleration, specifically the power spectral density function values for node 111. And then if you look here at this column, these are the frequencies, and here are the values for the Z or the T3 component or the third degree of freedom. Now, if we look at the function value 31.7 hertz, you see that we get 8.5 times 10 to the 6. So let's go ahead and confirm that real quick. So let's go ahead and reset this plot. So we're looking at the accelerations. We're looking at, let's go ahead and see. We're looking at node 111. So let's go ahead and display node 111. And if you look, here is our peak. The peak happens at 31.7 hertz. And it's 8.5 times 10 to the 6, which is matching this table here. Another thing. So here, that would be this line, line 903, 31.7 hertz, 8.5 times 10 to the 6. If you look at this other line, line 878, if you look at the last two columns, you get information about where the maximum is. The maximum, according to this, is happening at 31.7 hertz, and the corresponding value is 8.5 times 10 to the 6. And you get told the same thing for the minimum. Here we get told that the minimum is 7.58 times 10 to the 2. So maybe let's go ahead and do that. Let's go ahead and adjust the bounds between 700 and 750. Or actually, let me just move out of here. And let me redo this again. I've accidentally flipped the balance, so let me go ahead and fix this. So here we're going from 0 to 1000. I actually didn't know you could flip the balance. That's new to me. Okay, so we're going from 758, so that would be here. 758. And the value is about 9,305. So that's the same value we see here. So this would be the minimum at 758 hertz, and it gives you an acceleration of 9,304, which is the same values that we're seeing here in the table. Now for the second table, we're actually getting different values. We're getting the element stresses, specifically the PSDF values for element 1, the third component, if you will. So what does that look like? So if we go back to the plots browser, that would be the stress plot. And we're looking at this for elements, let's see, element 1. So let's go here and make sure that we've only displayed the graph for element 1. Let's go ahead and display the peak values. And here, if we look at this table, we get told that the maximum is happening at 31.71 hertz, and the maximum response is 1.45 times 10 to the 6. So if we look here, we get the same thing. At 31.7 hertz, the maximum is 1.45 times 10 to the 6. Now, what's the minimum? If we look here, we get told that the minimum is happening at 831 hertz. So let's go ahead and find that value. So that would be here, 831 hertz, and we get a value of about 0.22. And that's going to match the value that we have here also, 0.22. Now here's the same table of data. And again, this table was created with the XYPrint command. So here, XYPrint, I'll put the stresses for the power spectral density function values for element 1, component 3. So here are the same values, and now we want to look for frequency 831, because that's where the minimum is. So let's go ahead and find 831, so that would be here, and the value is 0.22, so that would be here. Okay, so that's the first example. Again, what I wanted to do was the following. I wanted to show you how to create graphs when you're working with results from a random analysis. More importantly, we had to make sure that what we got from Nastran and what we have in the F06 file, these are the same values that are used in our graphs. And then we went ahead and discussed how to interpret some of the commands that we see here, the acceleration, the stress, and the XYPrint commands. And this is going to be the first example for today. In the second example, that's titled Plate Subjected to Pressure and Point Load with Cross Spectrum Input, we want to create two plots. Now, the first plot is going to be a similar plot like before. We want to know the power spectral density function values for the acceleration at grid 28. That would be this plot. And then we want to create a plot for the autocorrelation values for the acceleration at grid 55. Now let's go ahead and do the following. Let me close some of these old windows. And I want to show you where node 28 and 55 are. So what I'm going to do is I'm going to upload the bulk data file for this other example. And let's go ahead and display nodes 28 and 55. So these are the two nodes where we want to create graphs for. So grid 55 and grid 28. So let's go back here and open up the HDF5 Explorer. Let's go ahead and upload the H5 file for that second example. So let's go ahead and run Nastran. Let's go ahead and select that H5 file. And let's go ahead and create this first graph. The PSDF graph for acceleration at grid 28. So let's go ahead and do that. So here we're going to select the acceleration data set. We're going to click create plot. We're going to click on last plot added. Let's go ahead and configure the vertical axes to use the log format. And if you look at this graph and compare it to the graph that we have here in the documentation, you can see that they're very similar. The only difference is the following. In the documentation for the horizontal axes, they use a log scale, but here in the web app, we're using a linear scale. What we can do is the following. We can take that data and output it to a CSV file. We can open the data in Excel, and then we can go ahead and create our graphs. And here, let's go ahead and modify the scale for the vertical and the horizontal axes. So here what I want to do is use a log format, and let's go ahead and repeat this for the horizontal axes. And then for the horizontal axes, maybe I want to start this maybe at 10 hertz. So let's go ahead and fix that. And then if you look at this new graph, this graph is also very similar to the graph we see in the documentation. So that's how you create a plot of the PSDF values for acceleration at node 28. Now there's a second graph here that's worth discussing. So let me close some of these windows. So the other graph they want us to create is a plot of the autocorrelation values for the acceleration at grid 55. Now, unfortunately, today the H5 format, so that would be this file here, H5, it does not support the autocorrelation values. So we have to resort to using the F06 file to get these values. So let's go ahead and open the F06 file. So if we scroll down a little, let's go ahead and scroll down here. We get this XY plot table. Here we see these are values for the acceleration, and they are the autocorrelation values. So here, this is the auto keyword, if you will. This is being done for node 55. And then I believe in the documentation, they want this for node 55. So this is what I recommend. Go ahead and copy this table. Let's go ahead and do this. And there are a lot of values, so let's go ahead and copy all of these values. And go down all the way to this line. Copy these values to a new text file. Let's go to the very top. And let's go ahead and delete the first line. And now let's go ahead and delete the 0. Let's go ahead and delete the text on the far right, the car number. And now let's go ahead and do this. Let's go ahead and add a comma here. So I press Control Alt, and then I use the mouse to select multiple rows and columns. And here what I want to do is scroll to the very bottom with the mouse. And what I want to do is I want to add a comma. And then I want to do the same for the other comma. Or column rather. So here, press Control Alt and hold down the mouse button and scroll down to the very bottom and add another comma here. Now what I'm doing is I want to create a CSV file, and then here I'm going to replace any space with no space. So let's go ahead and click replace all, and then let's go ahead and save this as a CSV file. So again, I want to create a CSV file of the autocorrelation values for node 55. So let's go ahead and save that here, and we'll go ahead and open the CSV file, and then I don't think I added a file extension, so let's go ahead and add CSV. And let's go ahead and do this. Let's select these two columns and select this plotting option. And you can see that this graph is now the same graph that we have here in the documentation. So that's how you create a plot for the autocorrelation values. Now again, for the power spectral density function values, we were able to use the HDA5 Explorer because all of the most of the random analysis results are in the H5 file. But when it came to creating the autocorrelation value graph, we had to resort to only using the F06 file. We have to go ahead and copy the text to a new text file. And then we have to go through this operation of adding commas and formatting the text. And then we have to go to Excel and create the final graph. So I think we're pretty much at the end of the video. Again, what I wanted to do in this video is explain how to create graphs after a Nastran random analysis. And then I wanted to summarize some of the output commands that you find in the case control section. So we went over the acceleration and stress commands. We also went over the XY print commands. We took a look at the HDF5 Explorer. We looked at all the different ways to zoom in, display the peak values, configure the legend to display different plots. Then we looked at how to use Excel to create some additional plots. Now, what's very important in this whole exercise is the following. We confirmed that whatever we saw in the F06 file, we also saw in the graphs. That's one very important step. This gives us confidence that the values that we see here in the graph are the same values that are being output to Nastran. Okay then, so we're pretty much done. Again, if you want to use the tools that you saw today, you can visit theengineeringlab.com. Here in the top right hand corner, there's a blue button. Click the button, fill out the form, and then you'll receive a link to download the software that you saw today. So with that, I'll stop here, and as always, thank you so much for watching.